The acidified oil industry uses vegetable oil residues, oil scraps, and waste oils as raw materials to produce fatty acids, oleic acid, stearic acid, and biodiesel through processes such as acidification, hydrolysis, and distillation. The wastewater generated by this industry is complex in composition and has an extremely high pollution load, making it one of the most difficult industrial wastewaters to treat in the oleochemical industry. Acidified oil wastewater is characterized by high chemical oxygen demand (COD), high oil content, high sulfate content, strong acidity, and poor biodegradability. Currently, engineering practice generally adopts a three-stage combined process of pretreatment plus biological treatment plus advanced treatment. Some high salinity projects also require the addition of an evaporation and concentration unit. The first stage is the pretreatment stage. First, floating oil and some dispersed oil are removed using an oil separator or flotation device. Then, lime slurry or sodium hydroxide is added to adjust the pH. Next, coagulants and coagulant aids are added to cause colloidal substances, fine oil droplets, and suspended solids to form large flocks for sedimentation and removal. For wastewater with severe emulsification of oil, a flotation unit can be added. The second stage is the biological treatment stage, typically employing a combination of anaerobic and aerobic processes. The aim is to degrade large amounts of organic matter while hydrolyzing long-chain fatty acids into short-chain organic acids, thus improving the biodegradability of the wastewater. The third stage is the advanced wastewater treatment stage, designed to ensure stable effluent compliance with standards. This primarily utilizes Fenton oxidation and membrane bioreactor technology to effectively degrade residual recalcitrant organic matter and decolorize the wastewater, further reducing the chemical oxygen demand (COD) and suspended solids concentration. For acidified oily wastewater with particularly high sulfate content, some companies use triple-effect evaporators or multi-effect evaporators for pretreatment after evaporation and concentration. The solids can be centrifuged to recover crude glycerol or sodium sulfate crystals, and the condensate is reused in production, with only a small amount of high-concentration mother liquor discharged into the subsequent biological treatment system. This combined approach of evaporation concentration plus biological treatment achieves resource recovery, while significantly reducing the salinity load entering the biological treatment system. Multiple domestic acidified oily wastewater treatment projects have shown that using a combined process of oil separation and conditioning plus coagulation sedimentation plus anaerobic plus aerobic plus advanced treatment can achieve a chemical oxygen demand (COD) removal rate of over 97% and an ammonia nitrogen removal rate of over 82%, with effluent consistently meeting integrated wastewater discharge standards or local discharge standards. In general, although acidified oily wastewater is difficult to treat, with reasonable pretreatment based on different components and combined processes, stable compliance with discharge standards can be achieved. Some projects can even achieve resource utilization through evaporation recovery.